大家好，我是王博老说半岛。Hi, folks. Today I'm going to continue my saga on the magic of semiconductors. So this talk will be given in English most of the time. I will sometimes interject with some Chinese to please my Chinese audience. Okay, bear with me. The title is The Magic of Semiconductors. Last time we did about yin and yang thing, right? Today I'm going to focus on so-called Gedanken moments or Gedanken experiments about the vacuum energy, the Fermi level, and then the charge neutrality level. All these three energy levels, I would like to have fun with them. So, okay, here we go. So, what is a Gedanken experiment? Gedanken is a German, and then if you split the word into two, Ger is to give, Denken is thinking. Okay, here actually it changed from because the way they pronounce it, they had to change the DEN to DAN because Denken is means thank you. Okay, that won't work, right? It's not giving a thank. Denken means that a thought process that you do imaginary experiment in your head, but it come out realistic. So it's an experiment using conceptual, not actual approach, but it total makes sense. That's the beauty of it. You have to make sense. Okay. And well, before we move on, let's have some interesting icebreaker for you. Here, the world one of the world most famous movie by Keanu Reeves. Now, I think most of people have seen this movie. I saw it a couple of times as well. And then in the movie, as you know, it's kind of a reality and dream at the same time. And then that our main character is confused whether he's in a dream or it's reality. It's actually part of the dream. He couldn't tell. Do you know that Chinese also have this kind of thought? In ancient time, it's called 庄周庄子, right? And there's a many famous painting, okay, about that. This is called 庄周梦蝶, meaning that he had a daydream and then he thought he was a butterfly. And then he woke up and said, wait a minute, I don't know, am I myself turning into a butterfly? Or actually, I am a butterfly, but in my dream, I am Zhuangzhou. See, that the dual reality is confusing to him. So he wrote a very famous article called, life is xiao yao yu means life is flowing like a river. And I would say that he had a creative, uh, he had pretty much had a creative dream. He had a creative dream, all right? He had a creative dream. And that's how he could be creative. The, pers- the purpose I mentioned these two because it seemed to me that the human creativity sometimes linked to dreams. In dream, they are most relaxed, and the creating popped up, right? Many great ideas popped up. I myself have some experience as well. I have a few inventions which happens after I have a dream. Right, some because my relaxation caused me to relax to be creative. Well, it happened to many people. Okay, one of the most famous here we have a very famous example um, by this great organic chemist, Kekulé. He dreamed of benzene and as a snake. See, that time nobody know how to properly write a benzene chemical form. And in his daydream, and he saw a snake seizing his own tail, right? Like this. So he said, well, and he put that into work and come up with a symbol, which we don't all use. This dream gave new doors to organic and chemistry, right? So I said he had a creative, again, this is not creative, sorry. So he had a creative Gedanken moment. And I think my message that we need more of this, right? And it turned out to me, well, there's another couple icebreaker. I'm going to show it to you. Descartes, Descartes demon, very famous demon, right? And that's the story is that he had many fancy dreams. This great philosopher, he thought that everything we saw, experienced in this world, they're all fake. Nothing is real. And even then one day he think maybe the mathematical formula like 2 plus 3 equal to 5 or 1 plus 1 equal to 2, maybe that's real. That's real. That's real. Everything else is fake. But then he later says to himself that, wait a minute, maybe that is still a fake. Maybe some super genius demons make him believe that 2 plus 3 equal to 5. So that's whole philosophy based on that. And so the Latin equivalent word for it is cogito ergo sum, right? So I would argue that Descartes' dream demons is a Gedanken dream. He envisions something in his head and he's trying to make sense out of it. Right? It turns out the way he thought everything is a fundamental of what science is built upon. Okay. And that's a good thing. I think that's how they make humans. We don't just believe everything we saw. We need to question it. So in Chinese said that I think, therefore I am. Right? 我思故我在. And cogito ergo sum. I like this, the sound of it. Right? The great Einstein had a thinking experiment as well. All right. I call it the invented thinking, creative thinking. He said that I'm in an elevator. If I accelerate as a speed of light, will I see the acceleration of the light? That's a question. Imagine if you're in an elevator and then and you will pull down by gravity, and then you don't feel it. While you're in an elevator, you won't feel it, right? Because you are isolated from your environment. But what about speed of light? What about this? You're riding in an elevator with speed of light. When you see the light crossing you, will that move the same speed as if the light stands still, or is still moving the speed of light? No, that's the question he asked. And he come out with this relativity based on his moment, his Gedanken moment, right? And this is a very interesting story. And Einstein was a little bit deeper. Okay. So my point is that understanding the thought process before internalizing them help us to become a great engineer and scientist. You have to feel how these great philosophers, great scientists, they come up with this idea. Why don't I have it then? Well, I need to dig into their mind, to their history, and understand a little bit more. Okay. For instance, I use here I have tried to study the famous Einstein story that he said that God does not play dice, right? Botanica, and and then I opened the website, and this is what I saw. Right? And then I use the bin here. Okay, I encourage you to use bin here, and then the Copilot, which is now turned to Copilot now, and you ask questions. When I'm reading it, I don't understand what this non-observant Ashkenazi Jew means. So I asked them, what is non-observant Ashkenazi Jews? So give me a detailed explanation and before understanding it. It's good. So these days, AI really help. Really help. I encourage you to use Copilot or ChatGPT. Copilot beauty, the Copilot is that they work on the same screen, right? You don't need to open multiple screen. They just appear with you. Well, that's the beauty of it. It is pretty good. Okay, and yeah, I'm not going to about recent lawsuit that Elon Musk suing the open AI, right? Because they become, the whole story. That's another story. So basically, I use that to further my study, to understand something better, to help me to understand the thought process, okay, of these great scientists. Actually, it really help us. It really help us. So my takeaway for you is that the curious mind is a must of a great thinking moment. You need to be curious. Why people do that? Why is that? Right? Let me give you an example. The created thinking moment turns the good to the great. What I meant is that you see, Schrodinger have this. He's a great, physicist. He had the Schrodinger equation that everybody knows and used, and he kind of make a mockery about the quantum mechanics. A lot of people using his equation to do a lot of quantum mechanical calculations. Okay, so he presented a test, live and death experiment. He argued that, well, according to your quantum mechanical theory, there's a state that there's a state that they could both exist at the same time. It could be dead or alive. And then he said, well, is that true? He's trying to make a mockery. But actually, his joke is no joke. His his Gedanken moment becomes a touchstone for the modern quantum mechanics. It is true. But the object exists in simultaneously different states until an observer occurs. Okay, so this is the fundamental right now. People understand, appreciate now. So his mockery, actually, his Gedanken mockery, become the cornerstone for the modern quantum mechanics. So that brings me to our topic. So what about vacuum energy, Fermi level energy, and then the charge neutrality level energy that we are all very familiar with in the semiconductor physics? Okay, so I want to go ahead and describe that one by one to see what do I mean by that? It's a Gedanken moment to me. Okay, it's all my personal belief, okay? So the first one is vacuum energy and Archimedean point. Okay. What I mean by that is that Archimedean point means that everything is reference to it. As we know in semiconductor physics, right? I last time talked about the yin and yang duality, and then what I meant is that one of the things I mentioned is that the EVAC is the ultimate reference, just like death, because all key energy parameters are referenced to an invisible EVAC. Here, we don't know what it is, okay? We just everything, the electron affinity, the work function, everything are referenced to it. And this is our ultimate reference. And the magnitude of these parameters against EVAC are the same for and after contact. And that's actually the fundamental things we worked we work against in developing our all kinds of CMOS operations or even all the physics behind it. Okay. And if I want to pull that in, what is the EVAC then? Okay. EVAC is just like a reference, right? It's the underlying background energy that the whole universe in space, we are banking on it. And it's a background energy. So people measure is 10 to the minus 9 joule. Okay, zero, just some kind of zero. And from a methodological figure perspective, it's Atlas. Okay, he, you know, he anchored himself. This is your EVAC. Everything he anchored himself and be able to hold the Earth. All right. I'm not the alpha, I'm the EVAC. Just make fun of it. Okay. What I meant is that Archimedean point is that, right? You remember this, right? That Archimedean point means that he could actually use the lever to give me a lever I could use to lift the Earth, right? That story. And this is the EVAC. We use that as our anchor, so as that we can all have this energy in a proper manner and not lay the foundations of semiconductor physics. Okay. And that's the EVAC is for. So the take-home message is that, well, yeah, it is a Archimedean point. It is a reference of all the interesting energy parameter that we are interested in. You have to internalize this in your head. So when you derive all these relationship between contact, between the Fermi level movements, you have to have this in your head. And then that's that's your fundamental point to anchor upon. Okay. So that's about EVAC. So let's move on. So what about Fermi level? Does Fermi level has a Gedanken origin? Okay. That will be my. Well, I mentioned this before, right? Fermi level is derived from the Pauli exclusion principle, that no two electrons can occupy the same state. That's said in a, fun manner that it has a very strict housing policy, right? And that two electrons can live in one house, one state. Okay, not there won't be another one coming in. With this fundamental, simple, idea that Fermi and Dirac can apply this strict housing policy to yield a Fermi Dirac distribution by using only 20 electrons. See that? This is what I did with Excel. You could follow this link to get exactly how it's been done. It just said that, see, two here mean that these depends how many electron you have, 20 electron, how many different state you could occupy, but each one of them can only two. So there's a how many different combinations you can have? Only about 24. And then you calculate the probability based on that. All right. So here, this is the one, that's 1 divided by 24, that's 0.02. Okay. And you plot it. Wow, Jesus. And that is your Fermi Dirac distribution. And the beauty of it is that you could use 20 electrons to follow this Pauli exclusion principle. With 20 electrons and 24 configurations, you come up with a probability distribution that fitting perfectly to the Fermi Dirac distribution as a form shown here. And you got Fermi level. Wow. So Fermi level is the energy that separates this probability by 1/2. Here is your 50%. Okay, your 50%. That is where the Fermi level energy resides. Okay, so you have E equal to EF, so this has become 0. So exponential that is 1. So your F function of E is 1/2. When the E is equal to EF, your Fermi level energy. And if you do it in a picture, you can see that for metal, the Fermi level is inside the conduction band. For the semiconductor, most of 95% of semiconductor, that the Fermi level is inside the band gap. You got to keep that in mind. The band, well, for the insulator, it's also inside and with a larger band gap. But why? This is forbidden band gap, right? This is forbidden. Why you define your Fermi level in a forbidden zone? That intuitively does not make sense, right? How can you define an energy level inside an area that no energy can be there, no electron can be there, right? What do you mean? So does that make sense? So And I'm asking you another question. Why electron drip under E field so fast in semiconductors, but not in metals and insulators? Here, slow, 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 fast. Why is that? Okay, before we answer this question, let's look at the data first. Electron drips in a semiconductor fast. You can look at the velocity saturation. Okay, just keep one thing in mind. Electron drips through metal wire is very slow, about 1 centimeter a second. But the average velocity of electrons in silicon semiconducting logic chip is 10 to the 6 to 10 to the 7. It's a million times faster. Okay, and this is a million times faster. And this is what's amazing. Why this happen? And only because that we want to use semiconductor as our logic chip. If it's not fast, who cares, right? Nobody going to use that for build any kind of chip. And why is that? Right? That I want to explore it through, you know, imaginary world for you, also as you, without going to too much mathematics, that just drive people crazy. I just want to give you some kind of a picture, right? For instance, how come electron can move so fast? Okay. And then you look at this is a block, the great scientist who said that the way the electron moves through the ions, the silicon ions, in a way that follow these special equations. This is their wave pocket going through here, and this color, green brownish stuff is the iso surface. So in this energy, everything is the same energy. So when you cross it, there's no energy lost, right? And and uh, and then that's they can imagine that the why electron can go through this when their energy space is inside in this iso surface. Okay, it's because you can imagine that when electron wave cross it, it's been squeezed, all right, by the ions in a proper manner. It's facilitated by the periodic potentials around them. So it moves very fast in a plane wave manner. And it does not lose energy that much. But but it only works for certain arrangements. I guess in my Gedanken moment is that the ions are massaging electron in a nice way. Okay, so because in a way the electron cannot penetrate through, right? Because it cannot penetrate, and therefore you have a band gap, right? And then your electrons or holes move through here. So it's a plane wave light. But you ask question, why, wait a minute, that copper can conduct very quickly, right? So what do you mean by that? Well, the electrical conduction speed of copper is 10 to the 8 centimeter per second because they have a very high electron concentrations. So conductivity formula is like this, all right? And then your mobility is slow, but you make it up with a high NC concentration. So, and then the electrical conduction of the semiconductor in contrast is actually small. Right, depends on your doping, of course. Okay, so this I'd like to give you a mind graph that. So when you imagine yourself with a think a moment, all right, I say it quietly. Oh yeah, it massages through it been massaged by the ions in the semiconductor. That's why, and through the iso surface, so it could move like a plane wave in a fast manner. In a fast manner. That's the beauty of it. Okay. So this is uh, this is how I envision how I try to explain block function in a mindset that's easy to understand, at least to me. So my Gedanken moment, I would like to share with you how well these are great guys who envision, Bloch is this great scientist envision and then put his envision into a mathematical form, right? That's what he did. So he came up with this beautiful equation, one of the most beautiful equations that Bloch equations, of course, to explain the Schrodinger equations. Very nice. That's his moment. How about mine? Well, mine is that this is, as a MOSFET, it's actually a mandrake reincarnation. This is a mandrake. It's a legendary plant, okay? Legendary plant. It looks like a ginseng, Chinese ginseng. Mandrake means that man plus dragon. An ancient word called Abdulu, right? It's devil's testicle. It's the world's most famous aphrodisiac in Western civilization. Chinese have similar thing. We call ginseng. Ginseng is a similar thing. They even look similar. Okay. I would say MOSFET is a reincarnation of Mandrake. He said, wait a minute, are you crazy? What do you mean by that? Right? Well, look at this. Right? You look at this, what that reminds you of, right? What it reminds you of. This is called raise the CG, raise ESD and ECG. You tell me this does not look like this, right? Yeah, somewhat look like that, right? And then if you squeeze it very hard, CG squeeze the channel very hard, it go faster. Tell me it's not, right? I will not say out loud here, but what this reminds you of? That's the mandrake, okay? And FemFat is also a mandrake in my Gedanken tree. Look at this, right? It's the same thing, okay? This is the fan, and this is the two balls, right? And then that's how it works. I will show you a picture exactly how it works. And this is 22 nanometers, 14 and 10. That the thing get taller and taller, narrower and narrower. And this is a 5 nanometer TSMC. Wow, super rectangular, super tall, super thin. Man, this guy good. What I meant is that, it has a mandrake because it has a climax, right? This is what mandrake can do to you. You look at how the MOSFET works, right? When you apply enough bias, when you apply a bias, you bend the bend at the edges. When you bend enough, you have this so-called inversion to the gas inversion. And what is that? And that's exactly here. That becomes when your VG is over your VT, your threshold voltage, the inversion happens, right? Your inversion charge happens. Boom. This is your electron inversion. That's exactly what happens. And here is your channel. And the whole MOSFET business is rely on how we control this off and on at will, like up to gigahertz, right? Right now we're in a couple of gigahertz range. And that is what silicon CMOS is doing. M and P can do this at the same time. And so I call it the climax at VG greater than ET is a 2D gas inversion. This is what Mandrake can do to you, right? Am I right? So bear with me. That's my Gedanken moment. Okay, I prove to you that's the way it works. Then what about the Gedanken movement? I would say the Fermi level movement is a Gedanken movement for a double E guy. Right? What do I mean by that? The Fermi level in semiconductor. Okay, it's not in metal, right? It's semiconductor. And let me go explain why is a Gedanken moment for an EE guy. Right? The Fermi level is a 50% line anchor point for device operation. Okay, now we explain that carefully with our Fermi level equations, right? Yeah. 50-50 meaning that, probability below it and above it, 50% cross point, 50% cross point. That's where the Fermi level resides. All right. But it's always fixated. It's fixed in a semiconductor by doping. We change the doping, we fix the Fermi level. Okay. And this in a semiconductor, we call it, all right, what do we call this? We we have this. This is the in a semiconductor, Fermi level in a semiconductor. But if you talk to the EE guy, they all treat them as if they are always moving. But I would say now people, the double E guy, treats them as if they were always moving. Well, that's strange, isn't it? That's very strange. Let's take a look at what's happening. Okay. Basically, when we apply a gate voltage to a metal, and this is our oxide, right? Then we induce the charges at the other side. All right. And when we put more and more the gate voltage, eventually we form, as we said before, the 2D gas inversion. And during this whole thing, the Fermi level on the metal side does not move at all, right? This line is sitting here. These are sitting here. Nothing is moving. So what is moving then? Moving is the bend edges. This part is bending more and more because it's been a bit influenced by the applied gate voltage. That's what we want them to bend. And then when you bend enough, we had this inversion. So this is what happened when we bend that enough. You have an inversion happen. And that's what, it should do. The whole idea for bending. So that's what I meant that. The gate voltage is forcing H, EC, and EV to bend. But so what is Fermi level pinning about? It does not make sense. Fermi level is already pinned. It cannot fix, right? I keep saying that. See, this Fermi level, this obviously is a p-type because doping move from the center to here. The more p you have, the closer it's going to see the EV band edge, the EV edge. So this did not change. This did not change, right? This did not change when you are applying external voltage. What's happening is this: your band edge changes, but this is difficult to handle. So EE guide do this. All right. So, well, what's the formula? So E guy do this. E guy said, well, if I'm sitting at the band edges, if the observer is the band edges, right? I shift the observer to the ECEV edge, then he will see the Fermi level is moving closer and away from it, right? Remember, like initially he sits here, and then you can see Fermi level in the semiconductor are very far away from it. But when he apply, well, getting closer and closer, or even cross it more. So if you imagine the observer is sitting at the band edges, then you do see the Fermi level moving because the band edge does not know he's moving. Assume he does not know. So with that perspective, EE is measuring the Gedanken thought process. Then he convinced that other people Fermi level is moving. Okay. In reality did not move. Okay. In physical sense, it did not move. But in a EE guy, mentally, when he described a Fermi level movement for his semiconductor, Fermi level seemed moving. So that's his Gedanken moment. Then what do I mean by Fermi level pinning? Okay, that means that it's not bending, right? We want to by the way, the Fermi level in the metal side, it move perfectly with VG. It can never be pinned. It always move, 1 volt to 1 volt. But in the Fermi level side, it's a semiconductor side. It cannot be adjusted. It can only be adjusted by doping, right? It cannot move around. So, what is the Fermi level pinning? I turn it. This is my Gedanken moment again. ED of a VG. ED, you have to check online what it means. I will not tell you here. All right. So when VG want to change something, want to change, want the bias, want to bend the band bending at the band edges, he cannot. Right? He wants to have a climax. He has problems. And that's the ED. Okay. So with that thought process in mind, Fermi level pinning causes band edges reluctant to bend. It will not bend. It will not bend and it will not invert. Or it would delay the inversion. So there are two ways of dealing with this. Okay. For a MOS and then a metal semiconductor contact, there are two parameters we can use. For MOS, I would suggest using surface potential versus the applied gate voltage. What I meant by that is that ideally, if you apply a gate voltage 1 volt, a delta, right, 1 volt, then the edge should bend 1 volt. But somebody at the interface, okay, do something, and then you cannot get 1 volt bending because your charges are stolen. Somebody robbed you, right? And then that rob you make the ECEV did not see the full voltage, right? The charge is not there. So it reductant to bend. So this become a measure of your Fermi level movement efficiency. It's supposed to be 1, but if you didn't get it, mean that somebody is stealing from you, stolen that charge from you. You need to find out what's going on. Okay. And then for the metal semiconductor interface, S factor is being measured. All right. This is the slope. Okay. So how much Shockier barrier height change with the work function metal change? What I meant is the slope here. The slope. Okay. You know, if you change 1 volt, work function metal, do you see a 1 volt change here? Oops, no. Silicon does not do that. Silicon, the slope is about 0.16. So the effectiveness of a work function metal change, which translates to your Schottky barrier height, all right, is only 16%. But germanium is far less. It doesn't even bother. Doesn't even change. We later explain why. Okay, but this has been observed, very nicely observed everywhere. And then you could you use the reference to find out that. So all these two parameters you could use to measure the effectiveness or the severity of the Fermi level pinning. Okay. So where are these Fermi level pinning coming from? Okay, that we need to find out. People believe that it's from the fundamental gap states, the interface. The interface went nuts. All right. And this interface has many unknown things here. I call it the devil's fingerprint. Okay? We later going to explore that more. And then Cowley and Tsai lead us this layer, this interface layer, any layer, any contact, okay, metal, semiconductor, name it, they all have this problem. They believe that it contains some kind of quantum dipole with a large weird E field that distort everything. Here, see, here is very periodic, okay, and here you lost the periodicity, and then you screwed up. That's how you form all this crazy stuff. And we're going to go a little bit deeper. What do you see? I find a nice picture, right? Because the metal, all right, it has this kind of crazy mix. Metal-induced gap state. The metal induce some of the gap states. All right. What I mean by that is look at the picture here. The metal projected density of state like a sharp knife cutting into the semiconductor, like this nickel dioxide, that kind into silicons. All right, you see that the damage, the wound, all right, that created by this That is tensile state, right? It's like a knife, right? And then charge is supposed to be incurred by Vg. When you apply a voltage, what that does, you're gonna do something to attract charges, and or in a semiconductor side to in the future make it try to make it invert, right? But it cannot. It's reduced by mix. So gate control is less impacted in tuning surface potential. If you put this into a typical MOS, metal semiconductor, they have the same thing, right? They impair device operation. So this is a fundamental problem. All the interface are intrinsically bad until you do something to it, right? So the result is that Fermi level pinning means edge ECEV bending is retarded, all right? And so what's the result? So where is your VT? That's the key message. You can say, okay, I let it retard. I don't care. All right, I put a little bit more voltage. Well, first of all, you cannot do that. The voltage you can apply has been limited. Right now, you're going to 0.65 volts already, not even 1 volt. You cannot even further reduce it. And then you will shift your VT, right? Your VT, because the turn on, the way it turn on being stressed, you could no longer have the original turn on with a high DIT, with a high the gap states. Okay. So the Fermi level is the imaginary but real line can easily be a part of Gedanken family. Imagine you have Fermi level defined as a 50% line that I'm showing here in a forbidden zone, but that's a real thing. Okay. And then so it's great that I really respect these scientists that come up with this idea. Use the Fermi level to describe the how the on and off of a device, how they can be turned on and turned off, how they can work. They have this to think mindset, right? So I would say Fermi level can easily be a part of a Gedanken family. You have to envision yourself to do that and then follow this great scientist mindset. And then it'll be easier if you comprehend that and move forward with your study. So that's a formula. Now let's go to more complex topic, which is the charge neutrality level. I would say that charge neutrality level is the anchor point for the free space. Okay. Fermi level is the anchor point for semiconductor, the space charge region. All right, it moves up and down. All right, let me remind you again. The Fermi level does not really move, right? In reality, so it's the anchor point. Everything is referenced to the Fermi level. So if you're sitting here, sitting anywhere, you look at it as if it's moving, yes, but the anchor point is Fermi level. This has to be fixed. Without that, no device can work properly, right? You fix your Fermi your Fermi level in a way to fit your device operation. Okay. So with that in mind, the anchor point for the free space is called the charge neutrality level. And that is more difficult to understand. Let me elaborate on that. Fermi level is fixated by doping, but what about charge neutrality level? Right? This you fix doping and it you fixed. Before we move on, let's do the simple reminding you about the origin of the band gap. This is the potential well. This is where the ion sits, right? So it's impenetrable. This one's impenetrable. So in electron travel, it cannot go inside the ions, right? So that one, and this is your ion Z plus. So that's why these potential wells infinity, you can never go through it. But that's very difficult to do mathematically. So the KP, these two guys, say, let's do this. Let's make it rectangular. Okay, let's make it rectangular. This dealing that with mathematically is easier with a range. And then you apply your Schrodinger equation, your block function, and you calculate it. Okay, and you find out, oops, there actually are two zones where you look at this equation. This is all sine, cosine, right? And you have solutions outside unity. This is unity 1, unity minus 1. And so everything is valid inside, but you have the mathematical solution that outside 1 and minus 1. And that is a forbidden zone. And that is the origin of EG, your energy band gap, because practically electron cannot penetrate through this. It's a probability of potential entry, but it cannot physical penetrate through it in a classical manner, but it can penetrate in quantum mechanics. Okay, but this way it's you did not actually really penetrate. What you do is as I explained earlier here, you you move it in a plane wave with the block functions. So your electron wave move across this iso surface, right? You don't really go inside the nucleus, right? You move along with it, right? Outside of it, in a way. And then this vibration, okay, the ion vibration, and it kind of massaging the electrons, and the electron can move very quickly, okay, in a selected case. Silicon can do that, semiconductor can do that, but not metal and insulator, okay? And so that's the beauty of the Fermi level. And then here I mentioned that the energy band gap come from these famous equation solutions. People, oh, here you calculated, and it's so silicon is 1.1 electron volt, but germanium is 0.66, right? But if I use a semi, and the reason fundamental you have the energy band gap is because the periodic movement or this periodic movement inside a perfect lattice. Okay, but when electron meets a free space, what happened then? You lost. See this periodic table, the bulk here, but you lost that periodicity, the periodic potentials, you lost at the edges. So the block wave has to decay. Once it decay, then there's no forbidden energy. The band gap lost. So the energy here in the KP space is continuous. Now what do I do? Okay. Inside, I have this Fermi level help me, right? But what about free space? I cannot have the Fermi level defined properly now. I need something else. And this is where the charge neutrality level coming in. Okay. Let's put a quick summary about that. The charge neutrality level separates acceptor-like and donor-like states. I will go more and more detail about that. See, this is where Fermi level, right? It resides into the energy band gap. But for the charge neutrality level, there's no EG anymore. There's no EG anymore. So how do you, in the K space, has no EG anymore? It has to be continuous in your K space, right? So people think they start to have a Gedanken moment, right? They say, hey, you gotta have this in a surface state region. Okay. What does it mean that the line above it, we call it acceptor, and then below it as a donor. We go later more detail about why they define that way. Okay. And then acceptor like means that when it's not occupied, it's neutral. Okay. Zero, it's not occupied. Zero. So, and then when it occupied, it's minus. I look at the picture here. You look at the picture here. You see electron, right? When you move, when it's not there, that your charge is zero. When we're going in, the electrons is a minus charge, right? So you could imagining this like that. So the guy who invented charge neutrality level is trying to borrow his picture. He had a Gedanken moment right now. And donor is the same, right? Donor is that when they occupied, all right, when they're not there, when they're there, that when they're there, if your hole coming here, when they're there, they fill it up, then the charge is neutral, okay, when occupied. And then when empty, so this is gone, the hole is gone, it's positive charge, it's magnetic charge. So you can see that the guy who invented charge in neutrality level is trying to borrow the idea from the Fermi level. Okay? And then this has huge consequences. Well, later we're going to explain more and more about this. I term it the charge in neutrality level and Fermi level are cross points. They are all cross points. All right. And then what I meant by that, the Fermi level are the cross point inside here. We fix this Fermi level. If we want to make it P, we go lower. We want to make it N, we go close to the EC, right? But it's fixed by doping. So, and then all the operations, all device operations are using that as a reference. And that's a cross point. Charge in neutrality level is the same thing. It's just describe the free surface. Right? We need that. We need some anchor point, some cross point. Okay. So, and the charge in neutrality level is the cross point between acceptor line and donor line. Here I meant is that it's separate here, and the sum of them is zero, as required by the charge in neutrality level. Okay, and then the Fermi level is a cross point that give you 1/2 probability 1/2, and then so that a given available electron energy state they occupy, that you could occupy, it's a probability thing. Interesting, right? It's not actually actual. The true population, you have to include other things as well. But Fermi level is just the probability give you Fe equal to 1/2. That's all, right? He had many other consequences. Here is defined this way. So it's a cross point, and it turns out very important to device operation. And then the charge in neutrality level, they want to follow, they want to copycat that Fermi level cross point idea and want to do something. Let's do a little bit deeper. Okay. Imagine you have a surface. All right. If nothing is in, there's no charge. There's no charge. All right. Initial state. So everything's neutral. And then when you do there's some equilibrium happen. This is the initial state. Then you will have the acceptor line trap on the top and field donor trap on the bottom, right? All these had to use empty. Empty is zero charge. Field and below it is donor like zero charge, so net is zero. And then the cross point that's how it's defined, right? So this will be equilibrium. They will change, they will rearrange initially no matter what you have. I said, wait a minute. If I initially have charges, well, then the charges will do the same thing. The ionized acceptor and ionized donor, they have to be balanced, right? The total charge is zero. So you must have equal number of donors versus acceptor because they're carrying different charges. And then initial state has to be also charge neutrality. Just it has to be held on by the charge neutrality. And then after you equilibrium, it has the same thing. Below and above it, is held by the charge neutrality level. They have to have the same configuration. Right. And then at the end of the day, all right, so you can imagine that the charge neutrality level has to work with Fermi level right now. And we'll later explain why. Okay. This is the beauty of it because we are imagining ourselves, we're imagining this, and this is not imagining, this is real, but we have to imagine it. It's a charge neutrality. Okay. The charge neutrality have forced the charge neutrality level to be formed in this manner. It can move around, all right? It can move around, but at the end of the day, you had to have a balance this way. Because at the same time, the initial state had to comprehend the charge from the space charge region. We're going to give you a clearer picture later what you mean by that, okay? And then the defect charge. before settling down with a new position of charge neutrality level. This level can move inside freely, but be constrained. It move inside the Fermi level. I mean, not Fermi level. Move inside band gap, but not exactly in a place you want it to be. It's a compromised position. Let me explain that gradually. It's not easy to understand, and then but they do our best to see where they can get it. So what's the difference between this charge neutrality level and Fermi level? Okay, it work in a different region. The space charge region is your Fermi level resides, right? The space charge region is a region you have band bending. Let me go back to the graph again. So the space charge region, meaning that this area where the band bending, this area, okay, you have former charge. This is the area. It does not here. It's only here. Here where you have charges, right? This region, x equal to some distance. Okay, here is where you have the space charge. You carry some charges. You deplete, you have ions there. That's where your space charge region. And that's where your Fermi level are talking about, right? You have this Fermi level, and then you have band bending, and then you move around back and forth, and you look at the Fermi level as if they are moving. That region, this region, is called space charge region. But the surface is a different story, right? Surface is a different story. Surface, we don't know how thick it is, right? We will discuss it later. But it's some narrow nanometer range. And it's messy, right? The surface of nothing only bounds. You don't know what it is, right? You don't know, you haven't dealt with it yet. Right? And then when that forms the surface state region, okay, you have the acceptor or donor that you have a line between them. So here we go. So charge neutral level is a simulation of Fermi level. You have Fermi level to anchor the space charge region. Then we measure in a protective manner, of course. Now the charge neutral level has no energy band gap, by the way, to handle the surface state region. You have to come up with some kind of a level, some kind of a anchor point, cross point, right? And this is how we define you. We need that so that we can talk to the space charge region. Otherwise, we cannot talk. They are combined, but we have to keep that in mind. The sum of these are being governed by one requirement, which is charge neutrality level. Charge neutrality. The net charge is zero. But what happens is not zero. Well, it's not zero, then something is flowing, right? The electron has to flow somewhere. And that's not what you want, right? The thing didn't heat up. It's still cold, right? The charge is somehow balanced by itself, crazily balanced by itself. Okay. Then we'll talk about how do we deal with this. All right. The surface becomes something different. It becomes charged. And in a specific manner. Okay. And actually in an imaginary manner. When you go measure, it's not there. Okay. But when you devise on it, you see it. Isn't that strange? Okay. Let me give you a little bit deeper. So where is charge neutrality level then? Okay, if you look at the picture on the right, on this paper, Asuba paper, very nice. Right? The surface state versus they're talking about two things. The charge neutrality level. Okay. When there's a charge, okay, then when Fermi level is above this, then it says that the electron, here it's empty and it's occupied. So when it's occupied, this is like electron occupied here is minus charge. So wait a minute. Why it's minus charge here? Well, because here, right? The sum of this had to be charge neutral. So when there's a positive charge accumulated, you will have the minus on the other side. This is, by the way, imaginary. okay, imaginary. When you go measure, you cannot find it. Just like you go take a semiconductor and you see, is that there's a bending? Well, there's no equipment to measure it, right? You don't know it's bending, how much it's bending, you don't know. But you do know it exists in a one-up device perspective. You will see that, okay? And here, when it's bending, you accumulate charge here, then you have different, you have this also the equivalent charge to balance, okay? And then here you have some DIT come into play, the defect, all right? All these things have to play together. And if you're doing this acceptor like, okay, your Fermi level is below this, all right, then it's below this, and here empty is your positive charge because this is, remember, we said it earlier here, that's how we define it. When you below this donor, when it's empty, it's positive charge, okay, because we look at here. When it's empty, the whole created is positive charge, okay, and then so this one is the same thing. So when it's minus accumulated, you have a balance of positive charge here, and that level is your Fermi level, charge neutrality level, and he has to say the charges actually will, in a way, show you where the charge neutrality level is. So the way to find this is very critical, right? So okay, I need to find it. So I will have to, then I can know whether my surface is being the surface state charge is this way or that way, because the relative position of Fermi level and charge neutrality level, that's the part I need to find out. I don't know whether my charge neutrality level is below or above. I need to first to find out my charge neutrality level. Okay, that is difficult part of it. And it turns out that you can find it. Okay, you can find it. How do you find it? Well, here is using germanium as example. Germanium, charge neutrality germanium using Schottky diodes. Right. What it did is that they measure the Schottky barrier by using different work functions metals. Different work function metal give you different response, and for another response, you could calculate the barrier height. All right. Here you have two reference lines. One is reference 0, meaning that everything is pinned. Your Fermi level complete pin. And here is complete unpinned. The slope is 1. For 1-to-1, for any 1 volt, right, to 1 volt here. So the line is a 1-to-1 line here. But in reality, you can see that this germanium line is very weak, very weak. Okay, so you come out with this this line. So the charge in neutrality level, all right, is reference to our vacuum. Remember our vacuum reference. Everything we do here are reference to the same reference energy. Right? And then here, this is what you measure. The phi 0. Okay, this one can calculate, and phi 0 is what you can find out. And then that is the tissue position or charge neutrality. But what you measure is this. Okay, the energy barrier of electron against the EC, all right, and then the charge neutrality level against the vacuum with this formula. This is the formula. This is done by Bardeen, all right, so people know that already. The usual relationship to and then the measurement, find out. You can measure this and then find out, oh, this is phi 0. That's the distance position of your charge neutrality level against EV. All right. The experiment is done this way. You find out the edge from the Schottky barrier high metals as contact. See, with different metal, all right, different metal, you have different response curve. A different response curve, then you could fit it. All right. And then this is what the curve you get it from. These are different here for these are famous experiment on different semiconductors. You can see everybody is less than 2, except Well, the best is W selenium tungsten 0.28. Everything 0.2 to 0.3, right? That's best you can get. Meaning that the work fundamental change is not that effective when you want to change the Sharpie barrier height. The best you can do is 20%, 30%, or usually less. Okay. And germanium is 0.6%, 0.03%. We showed that. I think we show it somewhere. Let me show you. Whoops. See here? Germanium is 0.03%. So you change work function metal, 1 electron volt, what you get is 0.03 electron volts. Kind of zero, horrible. Okay. But what does that mean? That means actually one thing. That means that germanium, okay, is very close to the EV here. EV here. And then this graph is 0.06. Somebody measure 0.09. Somebody measure 0.1. It's very close to the EV side. And this is many calculations, and it will show you more. It's kind of universal. Universal in a way that every material is different, right? And you cannot change it, pretty much. And then you look at the silicon. Wow, nice here. Okay. And well, Gerasana is good, but what happened? Well, we'll talk about that later. You look at INOS. Oh, INOS is inside EC. Oh, no. All right. That means that it's going to be very hard to make a PFET right here. It's not possible. And here you look at PFET. Here. Wow, here, yeah. So anything you close to the P side, you intrinsically can make a PFET, but going to be very difficult for N, right? And here is it's going to make a good, okay, pretty good NSAT. We'll explain later why. Okay, explain why. So this is experiments. So this experiment is trying to help you to find the S value, the slope of this one. And then so it's a measure of how bad the devil's fingerprint, the charge and trail level, does to your Fermi level pinning efficiency. The lower the value, the more pinning, the more difficult to move your very high or your VG, right? That's what I meant. And people now do a little bit more. They use actually initial calculation to find out. And then the charge neutral level comprehend free surface and defect surface state, and it's quite unique. So its position are fingerprint different. So I would say it's an intrinsic property. But when you're actually using it, it manifests itself on surface and interface. That's the strange thing about it, right? You don't treat that in a bulk because bulk got the space charge region, you got Fermi level there. That deal with it. You got your anchor point. You don't need that in your bulk. But charge neutral level is whenever you see an interface, a surface, boom, you come out. Okay. And this new new paper by Wally, very good. He says that, well, he's initial calculation, and he find out there's a standard hydrogen electrodes here, and it's a universal crossed everything, everything here. Okay, that's how you find out. And he calculated just by fundamental calculations. He's not using the experiment data that we saw here. He didn't use the experiment to do it. He used initial calculation and easily see that the charge neutral level he called it standard hydrogen electrode is sitting very close to the band edges, the valence band edge. That's exactly the one we observe here, right? Experimentally. and he calculated. And then all these value are actually matching the experiments. Very nice work. And even the water aqueous can fit in this model. Beauty, it's a beauty. So you can see that the charge and trade level is being dealt with, and then it seems people can find out where they are now. All right, they can find out where they are now and where they're coming from. And let's look at this paper. It's kind of interesting. It says that if you look at the density of state, the surface of germanium, it's very thick. It's very thick here. It's a peak here. All right, at EV band edges. You climb up here. But if you look at the silicon, it's kind of uniform. So I don't want to go in detail here, but basically it's from the ab initio calculation. And then because the way the broken bond works, right? The broken bond works. And then that's eventually come up with this. And also explain why the germanium's charge neutrality level is very close to EV side. All right, that's the reason. Because you see that the structure here give you a very high density of state here. Okay. And that's good and bad, I must say. And silicon is quite balanced. So in short, what I meant by charge neutrality level is that it's an intrinsic material property, but manifests itself as surface interface, right? But so, okay, then you said, so what's the big deal? The big deal is this. The device operates with a bad charge and trailer level. What I meant is that if there's a defect here, there's a defect in the bulk of the crystal, but manifested in the surface. All right. So here, then you'll find out the DIT of the surface interfacial defect, interface defect. It has this kind of huge peak here. And this huge peak, this energy, corresponds to this. All right. That's where this charge and trailer level resides. And you know where it is, but because there's defect here and they're pinned. Oh no. All right. So when the Fermi level, when you're dealing with this, when you're dealing with uh, when you're dealing with this movements, here is a minus charge or positive charge, depends on whether the reference position of the Fermi level and then the charge and trailer level. You say, yeah. I know what is the relative. If it's above, it's minus. It's below, it's positive. Yes. What's the big deal? The big deal is that DIT here is huge. Okay. Then the Fermi level and this pretty much when you apply a VK here, this one does not change because the charge has been forbidden or been retarded here, all right? Because it's a built-in negative charge there already. And you want to overcome that. It's a nightmare. It's a nightmare for the applied voltage to do that. Okay. And so I would say that charging the trail level is a guy with a hidden agenda and can be bad when misaligned with the formula. All right. Let's use another example to explain what I meant. What happened if charge and trail level and formula level are misaligned? Okay. If you look at germanium example, it's very close to the EV side. Stimulus measure is 0.1 volts, even though some people say it's not that much. It's only 0.6, 0.06. Let's give it that, right? Experimental error sometimes will not give you that much. Then your Fermi level, all right, when you initiate with a light bending here, this is where if you put Fermi level here, immediately you know it's a p-type, right? Fermi level here, meaning that it's a p-type. Initially, honky-dory, everything's fine. But when you put a voltage greater than zero, then the band bending going down, right? Band bending going down. Then immediately there's a charge. There's a wall. build up a negative wall that retards your motions, right? Or help your motions. In this case, the build-up benefit PFAT, it will generate charge by itself, and you want to bend bending, and you are bending easier. Here you bend easier. You might leak more, but that's a different story. But you bend easier, okay? With the applied voltage here, you immediately find help because remember, the Fermi level is above charge neutral level. So this is the minus here help you to bend more, okay? And that is the beauty of it. So PFAT work well. But if you are NFAT, oh, so I'm sorry, not NFAT, N germanium. If N germanium here, your Fermi level is here. Oh no, so yeah, easy to, it will be good for your PFAT, but very bad for your NFAT because you want to do the other way around. And that's not what you want, right? That's not what you're going to get. So this natural occurring this way that the Fermi level is above charge neutral level. It's give you a benefit of PFAT, but super bad for NFAT because it has the easily built-in negative charges. So therefore, industry has no germanium or SiGe NFAT, only SiGe PFAT, right? And it's happening in TSMC 5 nanometer because the PFAT germanium give very much higher mobility. So, but they don't use pure germanium. They use maybe 25, 30% roughly, right? For their 5 nanometer. Are they going to use it for 3 nanometer? I don't know. Should be, right? But it's not easy to do. It's not easy to do, to form a P channel. We have talk about that, right? We have talk about that, describing how it's done. And so this material property, the charge neutral level here, that's the built-in, that's the nature of germanium. And then your Fermi level has no choice but above that, right? Anything above that help your PFAT, but very bad for your MFAT, right? For MFAT, for your N germanium, you put it here, it's very bad because naked charges. So very bad for your MFAT. And that is because it's nature. So the relative position, okay, of Fermi level and charge neutral level and the defect would do a lot of harm or good to your device, right? In short, the Fermi level and charge neutral level are anchor points, interface, and speed surface. But remember, this formation is constrained by charge neutrality, right? The sum of all the device, the sum of all the contact, all the surface with this surface charge here, eventually, all right, you have to maintain a charge neutrality. So the whole thing had to be obeyed a charge neutrality. And this is a material property. Right? Once you pick a material, it's fixed. And here, you modulate it by doping. Okay. And then here is N gain. Okay, you put it formula very close to it. And then so when you have that, your formula you immediately create charges here. In a figuratively speaking, okay, you cannot measure it yet. All right, because this is the initial state. Final state, you have the bend bending. And then you could only envision yourself by a device operation. The whole thing is kind of imaginary, but they could derive it. Right? This guy expert can derive it and then make it as if they are real through this Gedanken mindset. It is real in the device operation, but you can measure upon device parameters, but you cannot actually go and measure it with a probe. It's not as straightforward. Okay, that's the fun thing about that. So, oh my God, are we having the Gedanken moments now? Is this the yin and yang thing? Is supposed to be mutually constrained? That's my fun story. Okay. Um, Today I read a story about AI. They say that a unified computational model, right, based on atomistic machine learning, okay, you could couple this learning to model the complete silicon oxide bulk and free surface and interface. Oh God, right? Very high pressure. This is salt high pressure phase, and then the free surface. Free surface. This is the most difficult part. I can model it. All right, and then the heterogeneity in the nanoscale. Okay, they can model it, and the model they use. This remind me of large language model. Right, they could dissect the initial data, and then they put machine learning to it. At the end of the day, they will fit the final model. Okay, this is kind of like machine learning. Let's not going back to the detail. This just come out today. Okay, I'm very impressed. The result is this. This is the classical uh, thermodynamic models that give you this detailed phase diagram, the temperature versus pressure of different phases. And this is using a AI, a machine learning tool to do that. They are so similar and not too far off, Mister. And these are much quicker, much more efficient, right? And this is amazing to me. Okay, so my challenge to you is that so is AI going to today conform me for us? Right? We have a great idea, all right? All these great idea, fancy idea, is going to be replaced by the AI, the machine learning model. So I don't need to deal with this. It could give me device, the way they use that AI model, give my device operation performance easily without going through the hoop. I don't. I really don't know. Well, God bless. Okay. So today I'm talking about my and their Gedanken fun moments with the EVAC, Fermi level, and charge and trade level. What I'm trying to convey is that all these come out with some kind of deep thinking with a simple thought like charge and neutrality level, okay? That forcing these two to align with each other. And this is the fundamental of all energies. And then if you look at the Einstein thinking experiment, the specific relativity saying that acceleration of light will not change based on your own acceleration. It doesn't matter. And that is the fundamental of the relativity. Okay. So it seemed to me that the more we have these Gedanken fun moments in our head, and we could run the mathematical formulas, and then the graph was showing all these great authors. I can really help you understand the device operation. Even though when we measure each one of them, you had to measure them indirectly. Okay, that's the fun thing about it. All right. Thank you very much. This is my talk here. Hope that helps.